I know very well that I was fast, okay? But as I mentioned, the purpose was not so much to explain all details, but to make those of you who aren't already aware of those kind of structures that you find in dynamical systems. And those of you who already know the stuff, maybe they have just seen it in a slightly different fashion. Okay, there are things that you find in many books. So someone actually asked me about the literature. So I put something in the box, in the Dropbox. Maybe this is on. No, because when I come here,
yes,
this is off. Yeah. I don't know. Let's see. But okay, something behind. But if it doesn't bother you, I try not to get too much on this side, because seems. Yeah, okay. Well, let me delimit our space. So, about books, there is a whole variety of books that you can choose, whether more mathematical or whether more applied and so on. Now, I don't remember exactly the titles of the books, but I remember some of the authors, so I write here some of the authors. Okay. Strogatz is one author. He has a book on dynamical systems and chaos. Then there is a group of 3 of my friends from Rome, Cencini, Cecconi, Vulpiani. They have another book on dynamical systems and chaos. I think that the title of the book is really Chaos. These are very good books. This has very interesting applications. This is a classical book. If you want deeper mathematics, then there is a book by Ruel that is called Differentiable Dynamics and Bifurcation Theory. Something like that. Still on the mathematical side, but a little different, there is Holmes and Guckenheimer. This is also about bifurcations and dynamical systems. Yeah, I mean, there are many. Still more on the mathematical side, you have Ricardo Magnet, that is about ergodic theory. Okay? In any case, if you want to know more, you ask me. Plus, you have the material that I gave in the book. So, maybe it's time I start. Huh? Okay. And those who come in case they ask me later. Okay, so now what I want to do is to start to build this probabilistic or statistical theory of dynamical systems. Okay? And I gave you the motivation at the end of the previous class. The motivation is that when dynamics get too complicated, you cannot make predictions. You struggle, you work as hard as you like. But if you have exponential separation of trajectories, so if you have positive Lyapunov exponents, then after a short time, you have to resort to a different approach, which is statistical. It is probabilistic. It is very precise what we will do. It's not that it is sloppy. For instance, for weather forecasts, I'm not sure about Jalandhar, but for weather forecasts, you have a Lyapunov exponent you remember the Lyapunov exponent appears in the exponential e to lambda t. So dimensionally, this is the inverse of a time, because the exponential must be taken of a pure number. So this is time, then this must be 1 over time. Okay? So for weather forecasts, more or less, you have a Lyapunov exponent of 1 over a week. So if you want to do predictions that go beyond the week, tough. Good luck. Okay? You have these weather services that they give you, even on my phone, they give you forecasts up to 10 days, sometimes up to a month. Okay, don't trust them. If they get it right, which is not impossible, it is because they rely on something else. And most, they could be relying on good luck. But you know the pattern of weather more or less in a place, so you can try to get something like that. The forecasts of climate over the years, that is a totally different story. Okay? It goes beyond. It goes beyond the possibility of studying dynamically things. But what they do, and you find it also in your phones, is they give you the probability that something happens. Okay? And then what do you do with the probability? Whatever you like. We warn you. Okay? We tell you, look, there is a probability of 99% that it will rain tonight. Then you take an umbrella. Then if it does not rain, they didn't say anything wrong. Okay? They didn't say anything wrong. Probability, this would also take another course of 100 hours, is a very useful, extremely useful concept of something that doesn't exist. Okay? There is even a British famous probabilist who these days has written a paper or has been interviewed, I don't know. No, I think he's written a book, maybe. And the title is something like, probability probably doesn't exist. But, subtitle, but it is a good thing to do as if it exists. So I will take you through this path. Okay? Remember that probability, I would say a little more than probably doesn't exist. I would say probability doesn't exist, which is what one of the greatest probabilists, an Italian, Guido De Finetti, has stated. It comes from the tradition of Bayes. Okay? Probability is a rational scheme, something that is in your mind, not something that you touch. In which sense it doesn't exist? It does not exist in the sense of this phone. It's not material. Okay? If you want, I have one paper I could give you to you about when probability turns material. If we are lucky, by the end of this course, I tell you something about that. Okay? It's not like a stone. Okay? If I throw you a lump of probability, it doesn't hurt you. If I throw you a stone, maybe you don't like it. Two different, very different. But nevertheless, we want to use probability as something concrete in those cases in which there is nothing else that we can do. Oh, I didn't, yeah, but I saw when I started. So in 1 hour from when I started, I will stop. We spoke about dynamics. So let's start again from dynamics. And see little by little how we end up having probabilities. Now, okay, better. Okay, so we need a few ingredients. One, we need some space, okay, that we call phase space, that is a subset of Rn. Usually it is a manifold, meaning a differentiable manifold, meaning a set which is very, very nice. It doesn't have sharp corners of things, okay? In which points move. So you take an x in M, and then you have a law. The law is x dot equals g of x, where x dot is the time derivative. Okay? Then time could be anything else. It is in an abstract sense. Okay? Then, under proper conditions, for instance, Lipschitz continuity in things, okay, but I cannot go into the theory of differential equations, just take it for good. In a compact differentiable manifold, the solutions exist if the vector field G is also smooth. Okay? This exists globally, so for all times. So we consider we are in this case. Then we will have an operator, phi t, that takes point in M and pushes them to other points in M. Okay? You take 1x here, and after a time t, it will have become phi t x. Okay? Which also belongs to M. Phi t is what gives you the solution of this, in general, system of differential equations, because you could have variables or something, okay, whatever they are. I told you often, I mean, not often, always, we want phi t composed with phi s to be equal to phi t plus s. And if t can be positive and negative, then you have a group of diffeomorphisms. And if they are only positive, t and s, then you have a semi-group. Okay? But we will take t to belong either to R or to the integers. To R is for solution of differential equation, like that one. Okay? If it is an integer, then it is for maps. Maps can be obtained from continuous things, but not necessarily. Okay? To be a group, we need that phi 0 is equal to the identity also. Okay? And then there will be the inverse. Okay. Now, the inverse, okay, in the case that we have this, is defined as phi minus t applied to phi t equals to phi t applied to phi minus t equals to the identity, okay? Because we have t plus s equals 0. So we have a definition of phi minus t, of the inverse. This property is already quite important, the existence of the inverse. There is one property more that is often used in context of physics, but not only, that is called time reversal invariance. Okay? Usually is shortened as TRI. Okay? Time reversal invariance make use of the existence of the inverse, but it is a stronger property than the inverse. And then I will try to explain what is the difference. So we have time reversal invariance if there exists an operator, linear operator, continuous operator, that is called involution, that takes points in M, gives you another point in M, okay, with this property that I applied twice is equal to the identity. Okay? I'll give you an example. Then, if time reversal invariance, if there exists an involution, okay, an involution is a unitary operator which has this property, if there is an involution such that the evolution forward in time combined with I, applied to any x, phi ti x, is equal to I phi minus tx. Okay? Why is it called time reversal invariant? So this is for all t, which could be all r or all z, and for every x in M. What does this property tell us? Well, you remember that I squared is equal to 1. So if I apply I on the left, I phi t I x, because this is a point of our space. Then this is a point of our space. So to a point of our space, I can apply I. Okay? I phi ti x is equal to I squared phi t, phi minus t. But then I squared is the identity. So it's equal to phi minus t. So what you have in this case is that if there is one such involution, then you can go backward in time without having to go backward in time. You only go forward in time. You apply I, you go forward in time, you apply I again. Where are you? Where you were in the past. You never went back in time. Okay? Don't let be fooled. You will find places where they tell you that you can go backward in time. Not us. Okay? Star Trek or the story of the Empire. Okay, I don't remember how it is called. Okay, there maybe you can go backward in time. Not us. But it is true that at the level of elementary particles, and even these days of atoms, they can do little tricks like this. They can do it. In any case, what you're actually doing is going forward in time. And then you have to have a smart operator I, which may be not trivial. And if I want to get younger, I can assure you that I is not easier to find. It's not easy. Okay. I have a picture in my notes that are there. What this should be read is something in this way that says, I have my point x represented by two things, by a point and an arrow. The arrow tells me in which direction I'm moving, and the point, okay, but x is both. X is equal to point, arrow. It's not just the point. So suppose I have a trajectory that does like this. So this is my x, and this will be my phi t x, a time t later, which means I have a new point and a new arrow. If I apply to this, if I apply to this x, I apply I can imagine that it is like reversing the arrow and keeping the point. Okay? So this is x, this will be ix. Now, if I go forward in time, oh, sorry, I wrote it incorrectly. Look, t and minus t are the same. They are just two real numbers. So I can put the minus here and the plus here because it is better. Okay, so I apply I revert the arrow, and then I go backward in time, and I arrive here. I arrive at I phi tx. What is this? This is a point and arrow, that if I Now evolve it forward in time, I come back to where I started. So it is a new initial condition that does the trick of going, in quotes, backward in time. Okay? It doesn't really do it, but that is the idea. So many dynamical systems have the property of being invertible. The inverse exists. And some of being also time reversal invariant. That means there also exists an involution with these properties. They can be used, okay? They can be used. For instance, if you have systems in a magnetic field, which is something of interest in plasma physics, for instance. Okay? A magnetic field requires a special eye, but I am the one who has found the eyes that are suitable for magnetic fields. Now, this is about dynamics. Now, what are we interested in? On the dynamics or on certain properties that evolve with the dynamics? What do I mean by this? Okay. The weather here today is a combination of the properties of all the molecules of the air, okay, that move around under the forces that produce the winds, okay, the variations of pressure and so on. So I could try to speak about what the molecules of the air do. But then when I know what the molecules of the air do, I don't know if I have to wear gloves or not. I prefer to speak about temperature. So temperature is not dynamics. Dynamics is what moves the molecules. What is temperature? Temperature is an observable. It is an observable quantity, maybe not with your eyes, but with the thermometer. Okay, its value can be computed. Okay, what is an observable? An observable is a function of the points of your space. O is a function that takes points in M and produces a real number. Okay? So the temperature in particular can take positive and negative values in Celsius, in the scale of Celsius. Okay? In the scale of Kelvin, it can only take positive values. Okay. Just a function like this, we call it observable. Now, what is temperature? You know, I think practically all of you, or perhaps with few exceptions, have never seen the thermometer that you had to stick under your shoulder and keep it for 5 minutes. Sivaraji, are you old enough to have known that thing? Yes? Yes?
Yes. Still we use, and the light also they are using. Now they are using 2. Sometimes they keep it, and now they are using lights.
Yeah. Well, in many countries of the world, in the West, the old one has become illegal because the liquid inside, mercury, okay, that is toxic. So you know what happened to me? Because I travel a lot, I went through the security for a plane to catch a flight. I was always carrying this small, okay, that say if I get sick, at least I check if I am or if it is all in my mind. Okay. They saw it and said, where do you go with this thing? I thought, well, I mean, this doesn't kill anyone. It's not a knife or whatever. No, gone. And that was the last one that we had in our house. So now only the pistol.
You can use watch.
You can use watch. Okay, so in any case, you know, the characteristic times of the motion of molecules are of the order of 10 to minus 10 seconds, or even shorter. And when you stay 5 minutes like this, it is practically an infinite time for a molecule. Okay? Because 5 minutes, okay, you have 60 times 5, which makes 300, right? 300. 300 seconds, okay, and you have 10 to the 10 events in 1 second. So it is a huge time for a molecule. So what is the temperature that you measure? But even in 1 second, even if it is just 1 second, you have had 10 to the 10 molecular events, and sometimes 10 to the 12, if not 10 to the 14. Okay? What has happened is that you observe an average property of the motion of molecules. Because in such a long time, molecules have explored a large amount of different states. And that single number, which is temperature, summarizes all those practically infinitely many states. So mathematically, what do? Mathematically, we define the observed quantity in this way. We say that the observed value is the time average of the observable O along the trajectory that started at a given point x, and that is defined as limit for time that goes to infinity of 1 over time, integral over time of the values that the observable takes along the trajectory, starting at x. Okay? So, phi s x is the point at time s. O is a function defined on M, so it takes a value there. If you integrate, you sum over all the values along the whole trajectory up to time t. Divided by t, you have what is called the time average. Now, we say that the observable is a function of the phase space, as it is called, that produces a real number, and that the observation depends on where you started, okay? Because if you started to average yesterday outside, you get a different number because you started in a different place, okay? Then you make the time very large. Oh, of course, in reality there are no infinite times, but I told you. Tell me if 10 to the 10 years wouldn't look infinitely many years to you. Okay. You see, in mathematics, we have a problem. Because if I write 10 to the 10 to the 10 to the 10, it took me 3 seconds, right? But this number doesn't exist. This has no relation with anything at all that you can find in the world. Okay? And so it is just so easy to draw. Power of the mind. So we would like to say 10 to the 10. But if we don't take the limit, the mathematics becomes very difficult. There are what are called finite size effects. If I don't take this limit, okay, and I do that, I say this is 1000. Very difficult. Very difficult. Not on a computer, however. And so, from when computers are available, finite size effects are being studied more and more. But mathematically, if you have to do calculations, you know what it means taking h goes to 0, and you compute the derivative. You know what it means taking t to infinity. But what it takes, taking t to 1000 is difficult. Okay? You have, because the corrections can be difficult to compute. So anyways, to make the mathematics easy, this is what we do. And most of the times, it is a very good approximation. It is not infinity, but it is a very good approximation of reality. the difference between the integral from 0 to 1 to 10 to the 10 divided by 10 to the 10 from taking the limit to infinity is not, you will never notice it. You will never notice the difference, okay? So the mathematics is good. But keep in mind that these days we look at small systems over small times. Okay, I was told that I work with nanotechnologies, for instance. Okay, there we have times this short and also shorter, and so we cannot take the limit to infinity. But that is where we start, and then we will get more. Now, you know, if the dynamics are like those that I drew, I didn't draw, they were on my slides, in the morning, where there are those big fluctuations that you don't know where you go, it means that computing this integral is practically impossible. It is still easier than other things, but it is impossible, because this thing will vary tremendously, and you don't have a way of following these things. Okay? On a computer, you can try to approximate as better as you can, but for instance, it would mean you have to use very short time steps, and that it will make it computationally very expensive, and there will still be errors that propagate. So it's a mess. Not impossible, because a lot of progress has been done, but it would be much, much better if you get an average from a probability. Okay? It would be much, much better if you can write that this thing is equal to an expectation value with respect to a probability mu of my observable O, where by this symbol I mean the integral of O of x d mu of x. If I can do this, and if mu is a decent thing, then we are much happier. Okay? Then we are much happier. So here is how probability comes in. If the dynamics is complicated, this calculation is impossible. And it quickly becomes impossible. But maybe it is complicated enough, and better be very complicated, that there is a simple mu that does the trick. You have to be careful, okay, a little bit of probability theory, that these two things cannot be generally strictly equal. There must be some exception. Okay? Because you see, here there is the dependence on x, while here you have integrated over all x, so the dependence on x is gone. So you will be happy if this is true, not for all x, but for most of x. So mathematically, most of x will mean mu almost every x, which means with measure 1. Probability full has measure 1. It means we are excluding a set of 0 measure, or excluding set of 0 mu measure. Okay? What do we mean by this? Now, let's see if I can use efficiently my fingers. Where did I put this? The cup. No, because then it gets dried. I'm sorry. I'm sorry. It fell. Ah, I made it fall. Okay. Yeah, I apologize. So what do we mean by this kind of language? It is there.
Yeah, it was small.
But you know, when I went to lunch, I finished lunch, and then I took my jacket to come back. I was like this. I was saying,
Okay.
"Where is my phone? Where is my phone?" It happens to you? What do we mean by a measure, by mu measure of a set? It means that we... that's the... okay, pen.
Yes.
Pen. Okay. It means mu of E... It wants to write of its own. I use the other board. I use the other board because I noticed that it writes things when I don't know how not to make it. Then switch it off, Sivaraj. Thank you.
I will try this.
Thank you. Yeah, see what we can do. So I take a subset of M, my space, okay, and by the measure of the set E, mu of E, I mean the integral over the set E of the mu. Okay? So that equality there of time average and phase space average, as it is called, will be good if the exception is a set of zero measure. Okay? When do we call it a probability precisely?
So now you can also use this. Yeah, now you are free.
Huh?
Yes. So now you can use that.
Okay. So now first I fill this one, and then that I know how to remove. Select.
Yes. Delete. Yes.
Huh? Okay. We call these integrals a probability if we have this property that 0 is less or equal than mu of E, less or equal than 1. Okay? I should say for every E subset of M, not any E, not any subset really, but for every E that belongs to an object that is called sigma algebra defined on M. Okay? A sigma algebra is written in my notes, but just tell you quickly in words, is a collection of subsets. That is not all the subsets of M, because that leads to paradoxes. Okay? If some of you are familiar with Banach-Tarski, paradox, for instance. Okay? So you cannot give the probability of all subsets of M if M is a continuous set. Okay? Because the property of continuum is beautiful and terrible at the same time. Okay? But you have to choose a certain collection of subsets, in particular a collection that is closed under unions and complement, up to infinite unions. Okay? Topology is less strict. So for all so you choose your collection. You choose it. You choose it on the grounds of the applications you want to consider. Okay. Then for these sets, if you have this, you can speak of a probability, adding that mu of the whole space has to be equal to 1. Okay. That mu of the empty set has to be equal to 0. A subalgebra, a sigma algebra always contains the empty set. Okay? And then you have to have this property. Mu of E1 union E2, if they both are in the sigma algebra, equal to mu of E1 plus mu of E2 minus mu of the intersection. Okay? This can be a very general notion, but you can think of it as volumes, okay? As volumes or areas of sets. Say this is my M, okay? I give it probability 1. Then what is the area of E1 union E2? In this case, the intersection is 0, and then you get the sum of the two. But if there is an intersection, okay, then if you take the sum of the two, you count this twice. So you have to remove it once. Okay? Now this makes a probability. Sets, subsets in the phase space can be associated with functions. Okay? In particular, with what the probabilists call indicator function and the analysts call the characteristic function of a set E, always in the sigma algebra, of X. And this function is defined how? It's defined as 1 if X belongs to E, and 0 if not. Okay? Then this integral up here can be reduced always to an integral over the whole space, because then mu of E is equal to the integral over the whole space of chi E of X d mu of X. Okay? This connection between sets and functions is very important, because sometimes it is easier to work with sets, and sometimes it is easier to work with functions. But these characteristic functions have a very good property, that linear combinations of functions like this are dense in the space L01 of M and mu. Okay, they are dense. They are called simple functions. Okay, you can write them this way. Now I can use the one in the middle. And the cap is here. So, there is a pen? This one.
That also you can use in
No, you said that. Okay. Well, if there is this, is better than if I use my finger. I think, we will see. You tell me if it is readable. What was I saying? Okay. Simple functions are functions of this form. I have to be careful, huh? The color.
Yes.
Black.
It is
or blue even.
yes, and if you want in here, I can make. Okay, this is recognition. Try cursor. Yes.
Okay.
Yeah.
Let's try again. Now, that goes away. That go. Okay.
Yeah.
Let's see.
Yes.
No.
In hands.
But let's make with hands. With hands. Okay. So. Okay. Now I know. Delete.
Yes.
Delete.
Yes.
Okay. So F pen. F simple of X equals to sum in K from 1, maybe it is a bit too thick, from 1 to n of complex coefficients psi k Okay, these are simple functions. Okay, the coefficients can be complex numbers. Okay, these functions, the set of all these functions is dense in the L1 functions, which are the ones I want to make it less thick. Okay. Sorry?
It's multi. If you make it pen, maybe now it may go with the pen with the same color.
Yeah, it doesn't matter.
Yes.
It doesn't matter. It's okay.
Yes.
It's okay. Because I don't want to keep people too long. Somehow it likes that one. Ah! No. Never mind, never mind. No, it doesn't matter. I use... okay. I just use my finger. Sometimes electronic devices are a bit disappointing, but typically the fault is ours.
Yes.
But I cannot blame Sibarashi because he did his best and I couldn't do any better. So if you take the set of all these ones, okay, they are dense in L1, it means that you can approximate every L1 function, which is more than you need. L1 functions are really too many. Okay? Yeah, a function is in L1, f belongs to L1 of m mu, if integral absolute value f of x d mu x, okay, is a finite number. Huh. Maybe you can do better. Yeah, it's okay. Maybe if you select...
Oh, we have black का कर दिया.
Huh. No, I got very small. You see? Yeah. In the meantime, I continue with this. But you have seen, okay? They are standard definitions. Okay. So, coming to this other side. No, but we had found a pretty useful equilibrium. So if we can go back to what it was, I can use it. It was fine, it was fine. Okay. Yeah, that's very good. Yeah. Ah. Ah. I see. Okay. Ah, nice. Yeah. I can move it. Okay. Okay, so let's put it this. Okay. Now, erase that. Okay.
Maximize, you can use like this.
Yeah. Okay.
Minimize, and if you wanted to move, we'll just touch it.
Yeah. Okay, perfect. Thank you very much. What you can do are two equivalent things. One is you choose the sigma algebra. You choose which sets you want to which sets you want to attribute a probability. Or you choose a function space. You decide which are the functions of which you want to compute averages. Okay? Because now, with these tools, well, it was on the board before, but okay, you remember that is it here? No. That I had the expectation of a certain function f as the integral over m. It was O, you're right, but okay, it is the same thing. Okay? So, if you choose a different sigma algebra, you are telling me that you want a different set of functions, because you can build your functions from simple functions that are taken from the sigma algebra. Or, if you choose a set of functions, it corresponds to a certain choice of sigma algebra. And there are sigma algebras that are larger, they have more sets, they imply you can make measurements, finer measurements, or there are fewer sets, which means you measure more coarsely. Analogously, you can have a bigger space, L1 is a very big space, or you can have a smaller space. For instance, the analytic functions, it is much less than L1. Okay? And still, analytic functions, from one point of view, are not good enough, because you like to have discontinuities, for instance. But from other points of view, even they are too many. Okay? Connecting the mathematics and the physics here is a bit tricky. Okay? Because, for instance, physicists will be happy with 5, 6, 10 observables. Any function space has got infinitely many. Okay? So you have to be careful. It's a little bit like the integral from 0 to 1000, okay, or from 0 to infinity. The mathematics wants to go to infinity, and the physics would stop at 1000. Often, they are indistinguishable. But sometimes they are, so you have to know. Okay. Now, you have, what do you do with the probability? You compute expectation values or averages. They are called expectations because it's what you expect. Okay? But often, an average is what you expect. In the case of the temperature, okay, what we believe is that what you observe is an average, but is also what you expect. Okay? So you use this kind of language. Choosing the functions is equivalent to choosing their expected values. So you can also decide to choose the expected values. Okay, like, well, I just said. Now, the question is, but if we have a dynamical system, the points that are in E will be moved by the dynamics to other points. Okay? So, you will have that, say, this is your set E inside the big phase space. Okay? And now you let time pass. And this point goes here. And this other point goes here. And this other point goes here. And so you have a new set. Okay? This set here will be, if it was an evolution for a time t, phi t e. Okay? What does that mean? It means that if I had some probability given to E through my measure, probability measure mu, this probability now is here. This is an assumption. Okay, we assume the points carry with themselves their probability, not points, sets, carry their probability with themselves where they go, under the dynamics. It is like thinking of a fluid that carries its mass as it moves. Okay? If say I take this glass, and in fact I need it. So you see the water that was here, now is in my belly. The mass that was here, now is here. Same thing with probability. Now, I need more. Now, remember that if I throw this to you, you get wet. If I throw you a probability, you don't get wet.
Yes.
Okay? It doesn't touch you. So this is what is called an anthropomorphism. Okay? Is our way of looking at things. We are used about material objects, and also the abstract objects of mathematics, we want to think that they are material. Perfectly fine, but remember, a stone hits you, hurts you, a probability doesn't. Okay? Water makes you wet, and in cold weather you don't like. A probability doesn't make you wet. But we want to use the same. We want to use the same. If we are lucky, this thing will produce something useful. And if we are not lucky, we'll have to change. Maybe I can go another 10 minutes. So,
Other ways, if it is not continuous, we can give a break. In the lecture, you can have 2 hours. It is up to you.
no, I think that if I take 10 minutes more, I will not be left much behind with what I had. So if you receive, because I started 50 minutes ago. So for 1 hour is another 10 minutes. Okay? And then we'll see, in case I take a bit of the tutorial. So with this idea, we can define the evolution of a probability. Okay? We define the evolution of a probability. How do we define it? We define it this way. In the first place, we introduce the pre-image of a set, phi minus ti, okay? Which is all the points in the phase space such that their evolution is in E. Okay, so they are all points, phi minus t are all the points that if you give them a time t, they will end up inside E. That's why it's called pre-image. Okay, you can do the pre-image of the logistic map. You have the parabola, and now you want the pre-image of this set E. Okay, it is the union of 2 sets. This one and this one. Okay, this and this are the pre-image of this. Because if you go from these points, you end up inside E. Okay? And because the parabola is not monotonic, then you have 2 sets that will join forces to produce E. Okay? So, first you introduce the notion of pre-image, and then the evolved probability is defined in this way. We have a new probability, new, because things have changed, of a set E, still a bit too thick.
Use the pen for doing that change. Because that was the thing I did not do.
It goes from 1 to 5. Maybe 1 is too. Let's see. Nu of E.
So you use a different marker?
It doesn't matter. Okay, it is okay. Okay, it becomes the integral over the set E of a new probability d nu equal to the old probability in the pre-image, which is the integral over the set phi minus te of d mu. It is this idea. Okay? Now, if I call this E, eraser. Ah.
Yeah. Click in the pen and use your
Right. Okay, if I say that this is the set E, then this is the preimage. Okay? If this is E, then this is phi minus TE, because the points that are inside here came from here. Okay? So what I've written there is, in E, I will have the probability that the time earlier was in the preimage. And this way, I define a new probability. Okay? Yeah, I still have 4 minutes. So, if we want it in terms of the sets, this is equivalent to tell, say, if I say that this change has taken place in time, then I could say that I had an initial probability μ0 and another probability at time t. And I will define the evolution up to time t of the probability exactly as I have. I will write mu t of E equals integral over E of d mu t equal to mu0 of the preimage, which is the integral over the preimage phi minus te of d mu0. Okay? So you see, now from the dynamics that moves the points, I have obtained the evolution of probabilities. So probabilities can change in time. So for instance, say the probability of some event today is something, the probability of the same event tomorrow could be something different for a whole bunch of reasons. For instance, think of a medical test or some medical operation. Okay, if I have been under surgery today, and luckily I have to have surgery again tomorrow, the probability that something goes wrong is higher. Probability is not the same. Probability changes in time. This is one mathematical rule to, if you know the dynamics, to decide how probability will change. Still keeping in mind that probability is not a stone. Okay? And this, and with this I finish this hour, and this has a consequence for the observables, because then the expected values of the observables will change in time. Okay? Because we will define, where is it? Mixing up my notes. I'll just go by heart. Okay, it doesn't matter. Okay, we will define the expectation at time t of my observable O as, now you can guess what, as the integral over all space M of the observable O of x integrated with respect to the probability at time t. Okay? Which in general can be different from the expectation at time 0 of the same observable. Okay, temperature at time t and temperature at time 0 should be defined as the integral over m of the observable is the same, but the observed value is different because d mu 0 of x may be different by d mu. Okay? There are situations in which things don't change. Okay? If mu phi minus Te equals mu of E for every E in the sigma algebra and for every time, we call this mu an invariant. Probability. And what does it produce? It produces that expected values don't change. E at time t of O will be equal to E at time 0 of O for every t. And for every O in the function space that corresponds to the sigma algebra or the function space that you have chosen. Okay? So we have, like for points, for the points that move, we had the fixed points, we have the invariant probabilities. The invariant probabilities are fixed points of the evolution of the probability. Okay? Now, this is a bit abstract. In the tutorial, we see how to do some things with this in simple cases. Okay? All happy?
All happy. Thank you, sir.
Thank you. Thank you for your patience. for bearing with me. Yeah, questions? Now, you find this in my set, it is a chapter of a book that I'm writing that is called Probability Something. It is in the folder.
Shall I share the complete folder with all the participants?
You can share the folder with whoever you like, yes. Yes, I'll be glad that people use it, yes. Yes. When do we reconvene?
3:45. Shall we start with 4 o'clock?
4 o'clock. Perfect. Perfect. In the lab. Okay, so we move our stuff from here. Yeah, okay.
So you please take tea and biscuits, and then we will again disassemble the lab. That is in 4 o'clock. This is the lab, PG computing lab. Just one thing off. This okay. Please arrange it. First you arrange it.
Yeah. I switched this off.